Hi everyone and welcome back to PrepFusion. I am Anish and today we will discuss about the efficiency of a transformer. So today we will start with the lecture 15 of transformers. Okay, so we will discuss about efficiency in transformers. Also we will discuss another term known as alt efficiency. These two are actually different things. And also we will discuss a bit about ratings of a transformer. How does the rating change depending on the voltage and current and other parameters. So what is efficiency? So efficiency is basically a simple ratio. It is a term that is a ratio of the output power upon input power. Remember, it is power, right? It is active power. So as it is active power, that means it will be the watt component. It will be the wattful component. We will not take into effect the reactive power component, okay, or the kVA rating. It is not according to the kVA rating. Got it? So one more thing, this we had discussed previously as well, that output power will be what, or what will be the input power. Like efficiency can be written in two ways. So first way and second way I will discuss. So one way is to write that my input power is the addition of the output power and losses, because of course someone has to deliver the power to for the losses, right? Who will deliver? You will deliver. Okay, so input has to deliver for losses and as well as the output power that will go to the load. So if I replace this P input in this equation, then efficiency becomes P out divided by P out plus losses. So in percentage we write into 100%. Okay, into 100%. Now if I want to write basically in other terms, right? If I want to write in other terms, I can write this as well, right? That is my P out is equals to the input power minus the losses, because losses will go away from the input. Whatever is remaining, that will go to the output, that is the load. So I can replace P out in this equation. So efficiency can also be written like this, that it is equals to P in minus losses divided by P in. Okay, so both roughly will give the same value. There might be slight variations. Okay, roughly they will give the same value. There might be slight variations. Okay, now what are the losses? So losses in the previous lecture we had already discussed that losses mainly include the copper loss and the coal loss. Steel losses I am ignoring for a fact for now. Steel losses will be just some very small amount and they will give you the values. You never have to calculate the steel losses. Okay, so mainly my losses are the copper loss and the coal loss. Okay, now how is coal loss dependent? That is what we have to find out. So if you remember, hysteresis was dependent on the maximum flux, right? That is Bm raised to power x and the frequency, and eddy current loss was dependent on the Bm square and the frequency. So it is proportional. So actually here, right, there is no effect of current, right? It is not current dependent, right? Because maximum flux in the core will be fixed when voltage and frequency is fixed. Generally we will not change the frequency. So that's why these are called as the constant losses. These are independent of load variations. Independent of load variations. Independent of load variations. Okay. Now, what's next? What about the copper loss? So copper loss we had already discussed that PCU was equals to I1 square into RO1 or I2 square into RO2. Okay, so I can directly say that it is I1 square into R1 or I2 square into RO2. So here it is directly load dependent, so it will depend on load. Okay, these are the things that you need to keep in mind. So let's now discuss, because I had told you that we have two formulas. So actually which ones to use, okay, which is better, which ones to use. So we will discuss about that. So generally, right, how do I find out the efficiency? By this P out by P in. So ideally, these two values should not change. Ideally, there should not be any variation. But actually, there will be bit of variation. There will be bit of variation. What will be the variation? So ideally, like there are two, these are the two formulas which are both, which will yield the same answer. But one is the actual true value, n true value, and one is the measured value. Okay, in measured there are two cases. So you are providing some input. So input, right, you don't actually need to measure. You don't actually need to measure the input, right, because you know how much input you are providing. So input is generally known to you. Input is generally known to you. Okay, but output, right, either there are two options now. Input is generally known because there is a supply that you are supplying, you know how much power you are providing. Output, there are two options now. Either you can measure the output or measure the losses. Both ways will work to find out efficiency. For efficiency, you just need two variables, not three. Okay, so measure output or measure losses. Okay, so what I can say is that true value, let's assume few numbers. Let's assume that in the case 1 I am measuring the output. Okay, measure output. So let us first write down the true values. So true value, let's say my input power is 1.1 kilowatt. My power output actual value losses are 100 watts, that is 0.1 kilowatt, and my P out is equals to 1 kilowatt. Okay, so the actual true value of efficiency will not change, right, that will remain constant. So true value of efficiency will be obviously output by input, so which is output is 1 kilowatt divided by 1.1 into 100 percentage. So this will be 1 divided by 1.1 into 100, so 90.9 percentage. 90.9 percentage. %. Okay, this was the case 1. What about the this was the true value, this is what I am expecting. Now what is actually happening, if I measure the output, so in measurement, right, there can be 10% error. There can be error. If you have ever performed experiments, you will know the actual value and the experimental results vary. So let's assume while measuring the output there is 10% error, that instead of reading 1 kilowatt I read 900 watts, so that is 0.9 kilowatts. I know 10% error is huge, but let's exaggerate things and see how much variation is there. So if I am measuring the output, the efficiency will be what? Again, it will be output upon input. So currently I measured 0.9, so it will be 0.9 upon 1.1 into 100 percentage. So this value will be 0.9 upon 1.1 into 100. So it comes out to be 81.82 percentage. 81.82 percentage. Okay, 81.82 percentage. This is the efficiency that I will get if I have a 10% variation in measuring the output. Let's say now I say you that no, don't measure the output, measure the losses. So if I measure the losses, case 2, I don't measure the output, I measure the losses, because for calculating efficiency I will need two variables, either loss input or output input. Any two works. So I will measure the losses now. Okay, So if I measure the losses, what will be the values? So values will be efficiency of the measured value this will be equals to basically so again what is the actual value of loss? 0.1 kilowatts, but again I will assume that there is a 10% error. So if there is 10% error in the losses, so the losses that I will calculate will be 10% of 0.1, that is I mean 0.9 into 0.1, so it will be 0.09 kilowatt, as there is 10% error. Okay, it should have been 0.1, but I am reading back 0.09. So what will be the formula? Formula will be output by input into 100 percentage. So this will be equals to output by input, right? So this will be equals to output is uh, output is what? Input minus losses divided by input into 100. Input is how much? Input is 1.1 kilowatt, that we already know, minus 0.09 kilowatt divided by input 1.1 into 100 percentage. So if I calculate this value, right, this will be 1.1 minus 0.09 divided by 1.1. So the efficiency that comes out to be 91.81 percentage, 91.82 percentage roughly. So one thing I see, in the first case the error is drastic. If there is 10% change in the measurement of the output, the efficiency percentage is also drastically changed. Huge error, right, with respect to the true value. But if there is change like 10 same percentage of error in the losses, the measured value of efficiency does not change much. It is near about 92%, 91%. So this is fine. This much error is fine. That is fine. So what is the conclusion? Conclusion is that as the percentage of error is same, because output is a large number, so measuring that, and even 1% error if there is, so the error, absolute value of the error will be huge. That can cause huge variations in the efficiency. But even if there is large percentage of error in the calculation of the losses, as the losses in itself will be very low, like almost 10% of the input power. So if there is 10% variation in the measurement of losses, it will not actually affect my efficiency much. It will not affect the observed value of efficiency. Okay, so there is less derivation. So this is a practical reason. Another reason is also there is less derivation. So this is one of the reason that you will understand that why actually we don't measure the output directly to calculate efficiency, why we try to measure the losses. So in the lab, if you have performed the experiment, you will see that there is open circuit test, short circuit test, and those are used for measuring the losses, the coal loss and the copper loss respectively. Now I hope it is clear to you why we don't, like, it is so simple, right? Efficiency is output upon input. Why don't we just directly measure the output? And input we already know, so just take the ratio. Why we don't do it? First of all, output is a very large number, let's say 1.1 kilowatt or 1 kilowatt, right? To have that rated measuring instruments, it is very costly, because output is 1 kilowatt watt meter. If you need to buy a 1 kilowatt watt meter, it will cost you very high. But losses will be, right, very low, like this 0.09 or 0.1 kilowatt. It is like 100 watts. So buying a 100 watt meter is much cheaper compared to buying a 1 kilowatt watt meter. So this is one of the reason. First reason is there is less derivation. That's why we measure the losses only. And second reason is the losses in themselves are very low amount with respect to the output. So I don't need to buy expensive measuring instruments. So I will write here the points that we generally measure the losses for computing efficiency. Okay, reason, first reason is that even even for 10% error in measurement variation in the efficiency will be lower compared to if I had measured the output, will be lower. Second reason is uh, even like buying like high rating instruments is costly, so losses will be lower amount, so that will be cheaper. So these are the mainly two reasons why we generally measure the like losses and not the output. Okay, so we can further write down this formula. So this was actually the values. If you see the like my efficiency of transformer is this, it is P loss is P core plus Pu, and like basically we ignore the stray and the dielectric losses, and yeah, this is the formula. Now I want to derive this formula further. I want to derive this formula further. So my efficiency is what? Efficiency is output upon input. Correct? Efficiency is output upon input, which is equals to output by output uh, sorry yeah, output plus losses. Okay, so if we remember what is my circuit diagram, do I have the circuit diagram here? I don't have the circuit diagram, so I will very quickly copy the circuit diagram somehow. I'm in 309 page. So where is the circuit diagram? Somewhere I can find the circuit diagram. 309 page. Okay, somewhere can I find the circuit diagram? It's very difficult. Okay, here it is. So this is but this is a multi-winding transformer, right? Anywhere else I have the equivalent circuit diagram? Where is the equivalent circuit diagram? Phasor diagram, yes, here we have. Okay, so it's here, right? Just this should be fine. So if I copy this, right, so okay, so this is my circuit diagram, like approximate circuit diagram, not the exact one. So from here we can derive few things. Okay, what is the copper loss and what is output? This is my output, right? This is my output. So it is V2 dash, like it is a load, this is the load connected. This is the load connected, and this is V2 dash and this is I2 dash. So what is the power consumed by output? This is the output power, right? This output power will be constant, even if it is referred to the primary or secondary, it will be constant. Currently, what is the output power? It is basically output will be V2 dash into I2 dash into cos phi 2. Power factor angle will not change, right? Cos phi only. So this is my output power. Okay, or you can directly write it as V2 I2 cos phi. Power will not change. Even if it is referred, it will not change. V2 I2 cos phi also you can write. Why? Because V2 dash will be what? V2 dash will be N1 by N2 into V2. Or sorry, I told you otherwise. N2 by N1 into V2, and I2 dash will be N1 by N2 into I2. Basically, N1, those turns ratio will get cancelled. Ultimately, it will be V2 I2 into cos phi only. This will not change. Okay, this is my output. What is my copper loss? Copper loss PCU will be I1 whole square into RO1. Correct? I1 whole square into R1, or you can write I2 whole square into RO2, whichever one is suitable. Both are same. Okay. What about the coal loss? The coal loss is just a constant number. It does not depend on the it does not depend on the what do you say, on the load current. So coal loss is just P core, it will not depend, right? I want to come to a very important relationship. So I can write here my efficiency will be, this will be output is V2 I2 cos phi, V2 I2 cos phi divided by P out V2 I2 cos phi plus the losses. Losses is copper loss is I2 whole square into RO2 plus the coal loss. This will be a constant loss, right? Okay. This can be rewritten. What is V2 into I2? V2 into I2 is actually the rating of the kVA rating of the transformer. Okay. So V2 into I2 will be the S rated of the transformer into cos phi divided by S rated into cos phi plus I2 whole square into RO2 plus P core. Okay. So now we can convert this into per unit. How can I convert this into per unit? So what is S rated? So S rated is basically into V rated into I rated. Okay, this is my S rated, correct? So now if I divide by S rated on both sides, here and here, everywhere, right? If I divide by S rated on both sides, so it is basically S base, right? Basically S base. So this will be on the top hand side, it is S rated. It is S rated, right? So I want to change this formula. How do I change? This is the rated one. Okay. Okay. So this is the efficiency at rated load. What is the efficiency at any current, right? Any random current. It is this one only. So one thing I know, at any load, right, I2 will be some X time I2 FL, correct? Full load current basically, right? This we have already discussed previously. So if I replace here I2 with X I2 FL, if I replace here, right, so it will be V2 into X I2 FL into cos phi divided by this will be V2 into X I2 FL into cos phi plus X square I2 FL whole square into RO2 plus P core. Okay. So this can be rewritten actually. So my V2, right? V2 will be what? This is V2 into I2 FL. What is V2 into I2 FL? Basically V2 into I2 rated FL is V2 rated. V2 voltage will always be rated into I rated. So basically it is the S rated. So it is X into S rated cos phi divided by this will be V X into S rated cos phi plus this is what? This is full load copper loss. So X square into copper loss at full load plus P core. Of course P core is independent, right? So this is the expression basically. Now we want to find the condition for X at which my efficiency will be maximum. X means the what amount of loading will give me maximum efficiency. That is what I have to find out. So x is basically loading. So I want to find out the percentage of loading for which I will get maximum efficiency. So I will differentiate this whole equation with respect to x. So del n del eta upon del x, this will be equals to this will be so I have to differentiate, right? So it's like a numerator upon denominator. So this denominator will be whole squared, basically s rated. Like, what is the condition for maxima of a function? It is I have to differentiate that function with respect to the variable and make it 0. So if I differentiate this, the bottom denominator will be anyway squared, which does not matter because ultimately it will go on the right hand side, get multiplied with 0. So it will be 0 anyways, but still let's write it. So this will be whole squared, okay, and this will be equals to, now I will differentiate the top one. So it will be s rated. S rated is a constant number, x is variable, s rated is vrms, v rated into I rated, that is a constant number, right? Full load current, so it is a constant number. So s rated cos phi will be there and multiplied by the this term, the bottom term, right? So this term actually will be there. Okay, I will run out of space, so I have to, okay, I will take it in the next page. Also okay, we have so little space, so we will actually run out of space actually, right? We can actually can I simplify this expression? No, this is also fine, whichever way is fine. Okay, no, I actually want to simplify this expression. Okay, that would be better actually. Yeah, why, I will tell you. So what I will do, right? This I will write like this. If I divide by x on both sides, on numerator and denominator, so this will be equals to s rated into cos phi divided by s rated into cos phi plus x. So instead of writing rated, right, I will just write SR, so that will be easier. So let me just write SR because I am running out of space. Cos phi plus x into because I have divided by x on both sides, this will be CUFL plus P core divided by x. Okay, so let me just keep it here only, that would be better. So if I differentiate this now, like this top term is just a constant number, so this will just be there, this will just be outside, basically this will just be outside SR into cos phi, and inside what will happen, this will get squared and I have to differentiate this term, right? Basically I have to differentiate this term with respect to x. So here this will be 0 because this is a constant number, and basically there will be a minus sign, right? There will be a minus sign because like this is just a term 1 by f of x. So 1 by f of x will be minus of 1 divided by f square of x into f dash of x, right? I hope you remember chain rule and all those things. I hope I don't have to explain these basic things. So this will be 0 plus PCUFL plus, sorry, minus P core divided by x square. So from here I have to equate this 0. So of course this is a constant number, this is also a constant, I mean this is varying with x, this will never go, like this whole thing will never go to 0, this can only go to 0, that is my PCUFL minus P core by x square must be equated to 0. So from here we get a very good condition that my x square into PCUFL must be equals to P core. Basically what this means is, what is x square into PCUFL? It is the copper loss at that particular load. So it is the variable loss, right? Variable loss. And what is core? It is the constant loss, right? This will not vary with respect to the loading. So basically at maximum efficiency, if I want maximum efficiency at that particular point, the variable loss will be equals to the constant loss. But remember that this thing is applicable for that particular condition when the voltage is rated. Okay, make sure to remember that my voltage here is rated, voltage is V rated. Okay, it is only applicable for that condition when my voltage is rated. Got it? Very important point, very important point. Okay, so my x, right, what amount of loading I need x will be equals to under root of P core by PCU FL, full load copper loss. So very beautiful expression we get. Okay, so what is the value of the maximum efficiency? What is the value of the maximum efficiency? So value of the maximum efficiency, eta max, I know my P core loss and the full load, like this variable loss and the copper loss, sorry, variable loss and the constant loss will be same. So if I write this as, let's write x square, this x square into PCUFL equals to P core equals to some iron loss I, or some any value P, whatever you want to write. So basically it will be equals to what? It will be equals to the x into S rated cos phi divided by whatever is the amount of loading, x is simply that, divided by the x rated into cos phi plus 2 into Pi. That's it. Okay, plus 2 into Pi. That's it. So 2 Pi is this value, right? Because copper, one will be copper loss and one will be the core loss. Okay, so this is the value basically, and this is the expression. Just this you have to remember that this is only valid when the voltage is rated. So when my voltage is rated, then only this formula, all these things will be valid. So it's very good thing to remember. So it does not matter, like we have not actually derived for power factor. So power factor is constant. Assumption is that my power factor does not change. Cos phi is constant. I was only checking with respect to the load. Cos phi is constant here. That is the assumption. All the other parameters are constant except the loading. Okay. So now what can change? Now if I differentiate with respect to the power factor. So this was the maximum efficiency condition when I change my loading. Loading is changed. So we'll write here loading is changed. Okay. Now let's derive for the power factor. If I want to derive with respect to power factor, what will happen? So the same expression I will again bring it back. Okay. So this actual efficiency expression I will copy. So everything is constant, loading is constant, but power factor I am varying. So now I will differentiate with respect to phi, because if power factor is constant, that means the angle phi is constant. So I will differentiate with respect to phi. So this is the case 2 where my phi will be variable. Here my load was variable. And of course cos phi is constant. Okay. Cos phi is constant, so I can write this will be equals to I have to differentiate with respect to phi, right? Power factor angle phi. So again, like can I divide by cos phi? No, I should not. So this value will be what? I have to differentiate, like I am not differentiating the denominator because I don't care, because denominator anyways will get cancelled once it will go to the right hand side. I am just differentiating the numerator. Okay, so this will be differentiation of cos phi will be minus of sin phi, and x is there, x s rated will be there, okay, into the denominator, into s rated into sr cos phi plus. Now my loading is constant. If my loading is constant, all this will be simply 0. Sorry, I'm not differentiating here, right? Sorry, this is just a term. I've also forgotten the differentiation. So this will be the term that I will write. So I hope you know how to differentiate quotients. So CUFL P core, and now I will differentiate the other term. This is the denominator, right? So minus, if I differentiate this one, so this will be again XSR into minus of sin phi. Now this is constant, right? This is constant because if I differentiate this with respect to phi, it will not vary. This will also not vary. So all this will be simply 0 plus 0 plus 0 and multiplied by this term x SR cos phi equals to 0. I am not showing you the denominator because it will be just denominator whole square, that will go on the right hand side, that will be simply 0. Okay. So what is happening here? I need to make it 0, right, for me to maximize the efficiency. So how will it go to 0? So what I can see is that sin phi is there, cos phi, SR will get cancelled. Okay. So this is, let me rearrange the terms. So minus minus is here, right? So this will become plus. So this will be x SR sin phi into x SR cos phi plus x square PCU FL plus P core, then equals to x SR sin phi whole square, right? X square SR square sin square phi. So not sin square phi, this will be sin phi cos phi. Okay, so ultimately x and SR gets cancelled here, sin phi also gets cancelled, this is cancelled. So my cos phi is varying. So what will be the value of the cos phi? So this will be x SR cos phi plus x square PCU FL plus P core equals to x SR cos phi. So this also gets cancelled out. So this becomes actually independent of phi. Okay, am I right here? Am I doing any mistake? That is what I am trying to figure out. Sin phi is here. Okay, cos phi gets cancelled. Okay, one thing can happen. One thing can be a possibility. Like instead of cancelling out, right? I should not cancel out actually, because this will become independent of this values. So one thing is a possibility that because everything will get cancelled out, I will not simply cancel out. So there is a possibility that this is equal, these two are equal if my phi is 0. So if my phi is 0, this is 0 multiplied by anything will be 0, this is also 0 multiplied by anything will be 0. So 0 equals to 0 is satisfying. So that means at phi equals to 0, I will have maximum efficiency. What do we mean by phi equal to 0? It is unity power factor. So at unity power factor, the efficiency will be maximum. Unity power factor means if the load is purely resistive. If the load is purely resistive, then the efficiency will be maximum. Okay. So these are the two cases. So if I keep on increasing so if I keep on increasing my power factor, that is zero point 0.4 to 0.8, the efficiency will increase, and at this particular loading the efficiency will be maximum. Okay, where the power factor is also 1, where the loading is also this value. Okay, got it. So if I increase my power factor, so cos phi, the efficiency increases. That means if I decrease my angle, power factor angle, the efficiency will increase, because cos phi and phi are inversely proportional to each other. Okay, one more point, initially if I increase my load, okay, the initially if I increase the load, the efficiency will increase, and after a certain point the efficiency will decrease, right? So this is the optimal point where the transformer will work at maximum efficiency. So these were the formulas basically that we discussed. Okay, so now I wanted to leave you with few homeworks. Okay, so this so when, if I want my maximum efficiency at rated condition, so if I want the maximum efficiency to occur at rated condition, then basically it means I want it at rated, so it is full load. So basically my x is equals to I upon I FL, correct? So it is basically full load. Full load means I will be IFL, so x will be equals to 1. That means x is 1. So if x is 1, I want at this load maximum efficiency to occur. So 1 will be equals to under root P core by PCU FL. Okay. So this value will be equals to my P core will be equals to PCU FL. Okay. So of course if the full load copper loss is equals to the coal loss, then the maximum efficiency will occur at rated load. Previously, what was the condition for maximum efficiency? Variable loss must be equals to the full load variable loss must be equals to the constant loss. If I want this condition to occur in the rated condition, that means x is 1, that means the full load copper loss, that is the variable loss, must be equals to the coal loss. Okay, the variable loss at full load must be equals to the coal loss. Got it? Just few conclusions I wanted to write down. So let's solve few very basic questions on transformers for efficiency. Right, this is the first question, where a 2400 to 240 volts 200 kVA transformer has core loss of 1.8 kilowatt. Okay, at rated voltage. So it is rated voltage, right? So make sure you know that if nothing is mentioned, obviously you will assume it to be rated voltage only, but make sure it is on the rated voltage. If it is on the some other voltage, right, whatever we have derived will be wrong. So you have to solve with fundamentals then. Okay, its equivalent resistance is 1.1, that means its RPU, right, it's 1.1%, that is 0.011, that is what its RPU is. Okay, then the transfer efficiency at 0.9 power factor. So when my cos phi is 0.9 and on full load means x is 1, okay, I equals to IPU is, what is the transfer efficiency? Basically they are asking me what is the efficiency at full this full load at 0.8 power factor. So what have we derived till now? So we have derived that my formula of efficiency was x S rated into cos phi divided by x S rated into cos phi plus I square I x square PU PCU FL plus P core. Okay, that is what we have derived, right? So how will I find out the full load copper loss? So one formula I hope like I have derived everything to you, that what is PCU per unit. PCU per unit, if you remember, it was equals to x square into RPU, if you correctly remember it, right? And what will be the PCU per unit at full load? Okay, so full load x will be 1, it will be simply RPU. I hope you remember this, right? So this will be equals to, like these kind of questions will come in ESC only because you have to remember the formula. Okay, so this will be equals to what? This is equals to RPU is 0.011. That is what my RPU is. So how do I find out the actual value of PCU? PCU full load, absolute value. Basically it will be what? It will be not per unit, sorry, PCU full load. It will be PCU per unit full load into the S base, right? If I multiply the base, basically I will get the actual value. So it will be S base is how much? The rated condition. It is 200 kVA transformer. So this will be PCU is 0.011 into S base, that is 200 kVA. So this will be basically equals to 0.011 into 200. So this is 2.2 kilowatt. Okay, 2.2 kilowatt. This will be the full load copper loss. I know the coal loss. Coal loss is 1.8 kilowatt. So I can easily find out the efficiency. What will be the efficiency? So it is full load, right? So it will be SR into cos phi basically. So SR is 200 kilo kVA. So SR is 200 kVA. X is 1, right? It is full load into cos phi is 0.9 divided by 200 into 0.9 plus the full load copper loss, that is 2.2 kilowatt, plus the coal loss, that is 1.8 kilowatts. So this value will come out to be, this is 180 upon 180 plus 4, so 184. So this value will come out to be 180 upon 184, so 180 upon 184, so 0.9782, and they have asked in percentage, so it will be 97.82 percentage. Okay, very good question actually. Not that simple because sometimes you have to use the formulas, but other than that it is fine, I guess. This will be 97.82 percentage. Okay, let's solve this next question. So in this question, we have to determine the per unit value of equivalent resistance of a 200 kVA single phase transformer, given that its efficiency at rated load and unity power factor is 98%. So efficiency at rated load, that is X is 1. So what is efficiency formula? X into SR cos phi divided by X into SR cos phi plus P Cu X square into PCU FL plus P core. Now they have told me that my I am operating at full load, rated condition and unity power factor. So that is equals to 98%. So this is 0.98 equals to 1 into SR. SR is 20 and it is operating in unity power factor. So this will be 1 only, divided by 20 plus this is PCUFL plus P core. Okay, so now this is one of the equation. Other equation they have given me that at half the rated load efficiency is 97%. So at the half the rated load it is 97%, that is 0.98 will be 0.5 into SR into 1. It is same power factor, they have not mentioned it's at different power factor, we will assume same power factor. So this will be 10 plus PCUFL plus X square into PCUFL, this time X is half. So this will be 0.25 into PCUFL plus P core, of course, will not change. Okay. So from here actually I will be able to find out the values, right? So from this equation, if I rewrite this equation, my PCUFL plus P core will be equals to so this will be equals to 20, and so 20 divided by 0.98 minus 20, so this is 0.4 actually, 0.408 kilowatts. And here, right, the value will be this will be 10 divided by 0.97 minus 10, so 0.25 PCUFL plus P core will be 0.309 kilowatts. Okay, so from here I can like subtract these two equations, so I will get back my PCFL. So PCFL will be 0.75. If I subtract these two equations, PCFL 0.75 PCFL will be basically equals to this plus 0.408, so 0.0987. Okay, so this divided by 0.75, actually my full load copper loss is almost 0.136 kilowatts. So PCU, this is PCUFL, right? PCUFL, full load copper loss. PCUFL is equals to 131, or let me keep it at kilowatts only. Okay, so one thing I know, that what is the per unit copper loss? So per unit copper loss, full load, PCUFL full load, just in the previous question only we actually wrote the formula. It is equals to what? It is equals to RPU, right? Full load, I am talking about full load because x square will become full load. So that is equals to here, right? How do I find out the per unit copper loss? I will divide this value with its base, S base. So this will be 0.1316 divided by the S rated, divided by the S rated. So this value will be S rated. So S rated will be 20 kVA. Okay, so this divided by the 20 kVA. So this will be very low value actually. So 0.1316 divided by 20 kVA. So divided by 20 and this into 10 cube. So it's like 6.58144 into 10 raised to power minus 3 per unit, or in percentage if I want to write, this will be 0.658 percentage. Okay, whichever one is suitable to you, you can write it. So this will be the answer for this particular question. Okay, now let's discuss about another topic known as energy efficiency. Okay, we will discuss about another topic known as energy efficiency. So what is energy efficiency? So there are two kinds of efficiency. This was like the instantaneous efficiency, whatever power it is consuming for a particular load, right? Now let's say you have a transformer, okay, and it is operating throughout the whole day, and of course like the transformer is near your home, okay, and it is operating throughout the whole day, and you also know that just at the morning around 10 a.m. most of the offices open up, so there will be huge demand of power, huge demand of power. Okay, and around like this after in the like lunchtime lights are off or something, so around 12 a.m. not 12 a.m. sorry, around like 1 p.m. to 4 p.m. something like that, the power demand is low, power demand is low. Okay, then again around 7 p.m. if you remember, around 7 p.m. the power demand surges up. Why? Because the lights, all those things turn on, right? Because the outside light, daylight is gone, only moon you have, so you have to turn on your own home light. So again the power surges, power surges. Okay, so that is the problem basically. That is the problem here, right? So the problem is, if I just find out the efficiency for this particular load, that is not enough. I should know how my transformer is behaving holistically throughout the day. It's not like if, okay, the efficiency of the transformer is this 97 98%, but only at rated load or only at full load, okay, and but at half the rated load it is like some 70%, something like this. Very bad, right? Because I will lose so much of energy here when it will operate in less amount of power. Okay, my handwriting is very bad, please ignore my handwriting. Okay, so that is the problem here, that is the problem. So how will I improve this problem? So there is a metric, so that we can judge a transformer with its energy efficiency. So what is that metric? So what we do is, let's say whole day will be given to you, these are the time intervals, and for this t1 time the loading will be x1, that is the loading fraction, and the power factor will be cos phi 1, and full load copper loss will be x1 whole square into PCFL. Coal loss does not change, and time changes, right? According to the times the loading also changes, the power factor also changes, all these things changes. Okay, that is it basically, that is it. So how do I find out the efficiency? So efficiency, energy efficiency or all day efficiency is known as energy efficiency or all day efficiency is known as the this power energy consumed throughout the day, right? So I can write the expression. So I will run out of space, so I need to add a page. So here, right, this will be basically, this will be x1 into s rated into cos phi 1 plus x2 into s rated into cos phi 2. This is the amount of power, but I am talking about energy, so this also will get multiplied into time. Power into time is energy, so this will be T2. Okay, and so on, like so on, it will go on like this, right? What about the bottom will contain this number. Okay, so it will be basically sum of xi, sr will be constant, cos phi I into ti, where I is going from 1 to 24, because in the day I will have like 24 hours or something, so for each hour I am calculating, right? Or I to n, any value, like I equals to 1 to n, plus the losses. Now losses also will get added, right? So copper losses will get simply added, so it will be x1 whole square into PCFL into t1, x2 whole square into PCFL into t2, like this. So this will be I equals to 1 to n xi into xi whole square into PCFL, okay, I to n, and of course the coal loss, right? Coal loss will be simply added, there is no problem with it. So P core is constant, that it will go from I equals to 24, I equals to 1 to 20, not 24, n, okay, whatever, how many intervals I have divided my day, that I will compute. So your formula, although I don't tell you to remember the formula, but like the expression comes out to be, energy efficiency is coming out to be this value, okay, this will stay at the numerator and this whole denominator into 100 in percentage. Okay, so this is the formula for the energy efficiency, just a new term, that's it, okay, nothing fancy, nothing new. Okay, so generally which one we will compute? So this was the, like, if my load is varying throughout the day, it would be best to actually compute the all day efficiency rather than just efficiency, because I cannot measure if the load is varying throughout the day, how will the transformer perform. So what you'll do, you'll go to the manufacturer and you know what is your loading demand in your city, in Kolkata or in Bangalore, anywhere, you know what is the loading demand. So you will have the graph, you will give this graph to the manufacturer, and the manufacturer will tell you which transformer to buy. Depending, you will calculate, the manufacturer will calculate the efficiency, all the efficiency, and whose all the efficiency will be the best, that transformer will be given to you. Okay, so basically these are the formula. Basically you can see this formula. So here, right, actually this is wrong, right. PCUP and all efficiency will be this divided by this. So actually this formula is wrong. So this is the formula. Copy this. Basically it is equals to PCFL into time at the load, PCFL 24 hours, because peak hour is coal loss will always be constant. So into 24 gives me energy in watt hours. It does not matter. This also you can do. Okay, sorry, this right here I will, sorry, I forgot to multiply the time unit here. Okay, don't forget to multiply by the time, right, because everything is in energy. So I have to multiply the time. So this will be Ti here, this will be Ti here, right, this also will be Ti here. Sorry about that. Everything will be energy. So this also will be Ti here. Okay, so yeah, now which ones to calculate? So whenever it is a power transformer, generally, like I'm telling you a theoretical point, if it is a power transformer, its main purpose is to transfer the power. Its main purpose is not to transfer energy or handle variation of loads. So if it's a power transformer, then we will calculate the normal efficiency, whatever we had discussed previously. Now if it's a distribution transformer, distribution is generally near your homes and stuff. So if it's a distribution transformer, then the best metric to calculate, right, is actually the all day efficiency. All day efficiency. Okay, because we have to understand the effect of variation in load throughout the day. Okay, so day and night basically. So that's why we will use the metric, performance metric known as distribution, like all day efficiency. Okay, theoretical point. Understood? So that was it basically. There are a few questions. So what? Okay, we will solve these questions as well. Okay, we'll actually solve these questions. So this lecture will go a bit lengthy, but you have to bear with me. Okay, so let's let's solve this question, right. So here, right, we have a 100 kVA transformer which experiences following daily load variations 8 a.m. to 1 p.m. This is the load, this is the load, this is the load. Okay, given that the transformer has no load coal loss as this, full load ohmic loss is this, determine the all day efficiency. So I can easily find out the all day efficiency, right. What will be the all day efficiency? So I will copy this load variation. Okay, so first of all, right, I will calculate the energy consumed all day. What will be it? It will be this first energy, that is this is how many hours? This is like 8 a.m. to 1 p.m. So this is 5 hours. Okay, 5 hours, and load is this much. But I will only calculate the active load, right. I don't calculate the reactive power. So it will be 5 hours into the load, that is 65. Okay, 65 kilowatt. Then I have for the next 5 hours, again from 1 p.m. to 6 p.m. the load is 80 kilowatts. So it will be 5 hours into 80 kilowatts plus when the load is from 6 p.m. to 1 a.m. So again it is another not 5 hours this time, it is another 7 hours. 7 into 30 plus again from 1 a.m. to 8 a.m. So it is another 7 hours. It is no load, right? So there is no loss. 7 into 0 basically. So energy consumed in the whole day, 5 into 65. So it is 325 plus 400 plus 210. So this will be equals to 610. So 400 and 400 and 610 plus 3 to 5. So it will be 935 kilowatt hour. Okay, remember the unit, it is kilowatt hour. So this much energy is getting consumed. So what is the energy in the copper loss? So you have to check the loading, right? Okay. Full load ohmic loss is this, but in the question, right? Okay, it is a 100 kVA transformer. If it's a 100 kVA transformer, power factor is also changing, right? So I have to identify what is the full load actually. How do I understand what is the full load? So if it's a 100 kVA transformer, so what is the volt ampere rating here? How do I find out? So what is x basically here? So here, right, I have to identify the x. How do I identify the x? So x will be equals to the load consumed divided by the S base, correct? That will be the x basically. Am I correct? Am I correct? Or am I not correct? Okay, what is x? X is basically I upon I full load. So if I multiply by voltage on both sides, it will be the volt VI upon VI full load. So it will be S of the load divided by the S base. Okay. So for this, right, I have to actually find out the x as well. So what will be the x here? So x here will be, like, first of all I have to find out the S load. What is the apparent power? So apparent power here will be 65 whole square plus 45 whole square whole under root. So it will be 79.05. So from here, what will be my x? X will be basically 0.79. Okay, so x1 is 0.79. How do I find out x2? So again, same thing I have to do. 50 square plus 80 square whole under root. And so here, right, my x2 will be, like, S load will be this is S load 1, S load 2 will be 94.34. This is in kVA. So x2 will be equals to what? 0.934. Now S load 3 will be basically 30 square plus 30 square, that is 30 root 2. So 30 square plus 30 square whole under root. So it will be 42.426. So x3 will be basically 0.424. Okay, so these are my x3. So from here I can easily find out my energy copper loss. So this is x1 whole square into the full load copper loss. So this will be 0.79 whole square into PCUFL. PCUFL is 1200 watts or 1.2 into the time, that is 5 hours, plus next time the loading is 0.934 whole square into the this full load copper loss 1.2 kilowatt into the time, that is 5 hours again, plus loading is 0.424 whole square into the full load copper loss into the time. I can take common the full load copper loss, then it is 0 only because load is 0. Okay, so I can take actually common 1.2. all these I can calculate. So this will be 0.79 whole square into 5 plus 0.934 whole square into 5 plus 0.424 whole square into 7. Okay, so this will be 8.741 basically. So this into 1.2 roughly is 10.4 0.488 kilowatt hour. What is the coal loss? Coal loss is very simple, right? Coal loss, E core will be like, how much kilo is it? Is 0.37 kilowatt into 24 hours, because it is a all day efficiency. 3 kilowatt into 24 hours, because if you add up the time, right, if you add up the time here, if you see the whole, okay, it's not going here, if you see I'm starting from 8 am and ending at 8 am, so it is whole of 24 hours. So this will be 24 hours, so this value will be 0.37 into 24, this comes out to be 8.88 kilowatt hour. Okay, so it is 8.88 kilowatt hour. So now I can find out my all day efficiency. It will be the total energy consumed, that is 935 kilowatt hour. 935 kilowatt hour divided by 935 plus 10.488 plus 8.88 into 100, because I want to calculate in percentage. So this will be equals to 935 plus 10.488 plus 8.88 into 935 into 100. So it comes out to be 97.97 percentage. 97.97 percentage. So this will be the answer of this question. So this is how you can calculate the all day efficiency. Okay. So now let's discuss a bit about this interview questions. How would using a winding material with higher electrical conductivity impact the transformer efficiency and heating? Okay. So if I use a material with higher electrical conductivity, that means its sigma is high. If sigma is high, that means its resistivity is low, that means its resistance is low. And what is my copper loss? Copper loss is I square into R. So of course copper loss will reduce. So that's why it is written here, copper loss will reduce. Improved efficiency, if copper loss reduces, same thing, right? If copper loss reduces, automatically efficiency will increase, because losses has reduced. There will be reduced heating, it will heat up lesser, so thermal stability will be there, because of course copper loss generates heat. Better load handling, transformer with lower winding losses can handle higher currents more efficiently without excessive heating, because if like copper loss is high, that means at higher loads I square R will be very high, that will cause huge heating, that can cause problem. These were the reasons why transformer efficiency is lower at lower loads compared to its rated load, and how can this drop be mitigated. Okay, so at low loads the iron loss and coal loss remains constant. So what happens, although if X is very low, the copper loss reduces, right? Copper loss is very low, but iron loss, right, is constant. If iron loss is 1 kilowatt, so even at full load, even at zero load, 1 kilowatt loss is still there. So efficiency worsens drastically, right? Because my efficiency is what? Efficiency is P load divided by P load plus the PCU plus P iron, right? Now I know at lower loads P load will be low, because load is low, of course the load will take lesser amount of current, so the power will be low, right? This will be low. PCU also will be low, but P iron will be constant. So if I see one thing, that the numerator is reducing, but denominator, right, Pi is very high still. So denominator is still constant, somewhat constant value. So efficiency reduces drastically. That's why it is lower in lower loads. How can I mitigate it? So one way to mitigate is basically reduce the iron loss. How can I reduce the iron loss? To use better core materials, high quality core materials, which can minimize the iron loss, optimize the transformer design. Okay, employ energy efficient transformers that is designed for fluctuating loads, use of load management strategies to keep the transformer operating more closer to the optimal efficiency range. So one way is you reduce the iron loss, other way is you don't go to that low level of load. You manage, you optimize your load variations so that you never go to that level of low load, right? X equals to 0.2, X equals to 0.3, you always stay around X equal to 0.7, 0.8. How can I do it? So India follows a grid system. So in grid system, the power is actually interconnected. So any generating station from Kanyakumari will be connected to Jammu Kashmir. So power actually can flow from Kanyakumari to Jammu Kashmir because it's a grid system. Okay, so people are there, very small people, they actually manage the power. Okay, from where to take the power, actually they manage the power. So that is the advantage of a grid system that we will discuss in power system analysis. For now you have to understand just this thing, how can I improve the transformer efficiency. So now we will roughly discuss about ratings of transformer. So transformer ratings are primarily defined in terms of voltage, current, apparent power. So these ratings depend on the insulation levels, conductor dimensions and cooling mechanism. Okay, so I just want to calculate that if I vary the dimensions of my transformer, how will the ratings change. So let's solve one by one. Let's first discuss about voltage rating. So what happens to voltage if the dimensions are scaled by K? Okay, we are only discussing about the dimensions of transformer. What will happen to the other ratings if the dimensions are scaled? So we are discussing about if all the dimensions of the transformer are scaled by K. So what are the dimensions? Basically transformer is a 3D figure, right? So basically it has length, it has this is like the depth or the width of the core, this is the length and this is the width basically. So basically if all of them are scaled, okay, my area becomes what? Area of the cross section. If length is scaled, L dash is scaled to K into L, and your breadth is scaled or depth is scaled, D dash is scaled to K into D, and your width is scaled is into K into W. Okay, so what will happen to A? What will happen to A? So area of the cross section A dash will be K square into initial area, right? Because like two dimensions are getting multiplied, so it will be K square. Okay, so area, if all the dimensions are scaled by K, area will be scaled by K square. Area will be scaled by a factor of K square. Now what will happen to the voltage rating? Let's discuss about the first thing, voltage rating. So what is the voltage equals to? If you remember, the induced EMF voltage E1 was equals to root 2 pi f phi max into n. Okay, of course n is not the dimension of the turn, it is just a number of turns that will remain constant. Okay, so what is phi m equals to? Phi m is equals to root 2 pi f bm into area into n. Okay, now the thing is that the maximum flux density that a material can support is fixed, right? So all these are fixed. Frequency of course depends on the supply, number of turns is constant, fixed. So area, so if I change the dimension of the transformer to K, then area gets scaled by K square, so voltage also will be scaled by K square. So my new voltage rating will also be scaled by K square, right, than the old one. So if I scale all the other parameters of the transformer with K, then the voltage also will be scaled by K square. That is what is written over here. Voltage will also be scaled, voltage will be proportional to the K square. Okay, this is another term known as like net area, because what happens, the flux actually does not flow through the whole core. There is no term known as stacking factor. So overall core area into the stacking factor will be the net area through which the flux will flow. Basically net area means the area through which the flux is flowing. Just a theoretical point, that's it. Don't have to get into too much of details here. Just the area through which flux will flow. Okay, area through which flux will flow. That was about the voltage rating. Now let's discuss about the current rating. What will happen to the current? Okay, what will happen to the current basically? So the current rating, right? Current rating is also dependent on the area only. How much area is occupied by the copper winding? So actually current rating I will just show you upfront because that is not that important. Just you should remember the current rating also will be proportional to the area only. Okay, that is it also will be scaled by k square. Why it will be scaled by k square? It will be scaled by k square because uh, like there is a term, there are few terms here, I will explain. So my transformer is here. Okay, so what like there is a limit to which the maximum current can flow. So current, right, like every wire will have its current density rating, right? So every wire, depending if the wire is very thick, right, if the wire is very thick, then of course more current can flow. If the wire is very thin, then less current can flow. So basically the current is dependent on the area of the material, okay, of the winding. So if the area of the winding gets increased, then current also will get increased. So if I am scaling the dimensions of the transformer, then also if I am scaling the dimensions of the windings, so basically I can say that I dash will be basically, if like if I scale area, if I scale all the dimensions by k, then area will be scaled by k square. So I dash will also be k square into I. Okay, so the current will be scaled by a factor of k square. This I want you to remember. That's it. I want you to remember. Gate, in gate this will not be asked. This is important for ESC. And there is another thing as well known as window space factor. I'm not going into that right now. Just I have just told you with basic intuition. There is another term known as window space factor. So window space factor, through window space factor actually you can derive it. Okay, I'm not going into that. Okay, I'm not going into that because that is not required for gate exam point of view. Okay, just you need to remember that, like, that is what is written over here, that window space factor is this. So if like the area gets increased, if the dimensions are scaled by k, then a1 and a2 will be scaled by k square. But ignore this. Okay, don't study this, this will not be required. Just remember this, that the current also will be scaled by k square, just like voltage. So if current is scaled by k square, voltage is scaled by k square, what will happen to the kVA rating? So kVA also will be, basically kVA is what? kVA is voltage into current. So if voltage is scaled by k square, current is scaled by k square, so kVA will also be scaled by k square into V into k square into I. So basically kVA will be scaled by k raised to power 4 into kVA. So kVA will be scaled by k raised to power 4. Okay, if all the dimensions of the transformer are changed by k, are scaled by k, then kVA rating of the transformer will become k square, k raised to power 4. That is the conclusion. That is the conclusion. Okay. Now what about the co-loss and no load current? So if you remember, what was the no load current equals to? So if you remember, my no load current, right, was equals to N into Im. The MMF was equals to the flux phi m into the reluctance, like divided by the reluctance, right? This was the no load current. So what is no load current? No load current Im is equals to S phi m by N. Okay. So basically flux is constant. If I assume flux is constant, because voltage and frequency are constant, so flux is also constant. So assume phi m is constant. Okay, not phi m, sorry, bm. Assume bm is constant. Okay, assume bm is constant. Okay, because I want to convert this into bm only. Flux density generally of a material is fixed, right? Maximum flux that it can pass through. So bm is constant. So I will convert this into bm. So this will be s. S is L upon mu a into bm into a divided by n. Okay, so this will be equals to bm into L divided by mu, basically into n. So basically, right, my magnetizing component of the current is directly proportional to the length of the core. length of the mean length of the flux path. So Im is directly proportional to the mean length. So basically, if all the dimensions are scaled by k, so Im dash will become k into Im. So Im will be scaled by k. If all the dimensions of the transformer is scaled by k, then Im also will be scaled by k only. Okay. What about the this core loss component of the current? What about the core loss component of the current? So core loss component of the current, sorry, what is the like core loss? So if you remember core loss, right? In both the cases, core loss was proportional to the Bm, it was proportional to the x, f, and it was proportional to the volume, right? If you remember it, okay. Like I do understand that here some power of Bm was different, but assumption is that my Bm and f are fixed, right? If Bm and f are fixed, that means my core loss is directly proportional, because both the hysteresis and eddy current loss are proportional to the volume, and Bm and f are fixed, so core loss is directly proportional to volume. So basically what will happen, if all the dimensions are scaled by k, then the core loss also will be scaled by k cube. So P core will be scaled by k cube into previous P core. Okay. So that is what is written over here, that P core will be scaled by k cube. Okay, no load current will only be scaled by k. Okay. So this is a summary. Go through, you can go through this, and these are this is another question actually that came in GATE 2012. So in single phase 10 kVA 50 Hz transformer with 1 kilovolt primary winding draws a 0.5 ampere of current and 55 at rated voltage and frequency at no load. Okay, so at no load it draws a current with 1 kilovolt in the primary. Okay, at rated voltage and frequency at no load it draws 0.5 amperes of current. Okay, at rated voltage it draws 0.5 amperes of current. So okay, so my IO no load current is 0.5, and the power is 55, so that is the core loss, right? P core is 55 watts at a rated voltage and frequency. Okay, a second transformer has a core with all its linear dimensions √2 times the corresponding dimension of the first transformer. So basically a second transformer is there, but all the dimensions are scaled by √2. So if all the dimensions are scaled by √2, that means my k is √2. Okay, k is √2. Now what they're asking, the primary windings of both the transformers have same number of turns. So some same number of turns is there. If a rated voltage of 2 kilovolt at 50 Hz is applied to the primary of the second transformer, then the no load current and power respectively are. Okay. So if a rated voltage of 2 kilovolt at 50 Hz is applied to the primary of the second transformer, okay, 2 kilovolt is applied at the primary of the second transformer. Okay. Then the no load current and power respectively are. What will be the no load current and power? If a rated voltage of 2 kilovolt is applied at the primary of the second transformer. Okay, so one thing we know, that rated voltage gets scaled by k square, right? So that is actually correct. So voltage gets scaled by k square, so voltage will be scaled by twice. So V dash will be, new rated voltage will be twice the previous one. Previous rated voltage was 1 kilovolt, now it is 2 kilovolt, which is absolutely matching. Okay, what will happen to the current? So current also gets scaled by no load current gets scaled by k. This we have derived, right? So this current was the load current rating k square. No load current gets scaled by k only. So no load current will be scaled by k into previous one. So it will be √2 times the previous one. So √2 is 1.414 into k into the no load current, that is 0.5, right? So this will be basically 0.707. So 0.707 is present here. Okay, and they're asking the power. What will be the power? So core loss we have already derived. What will happen to the power? So power, right? Power will be scaled. The core loss component of the power will be scaled by k cube, because it is proportional to the volume, right? P core is proportional to the volume, if you remember. So it will be scaled by k cube. So P core dash will be k cube into P core. So this will be 2 root 2 into P core, that is 55 watt. So this value will be 55 into 2 into root 2. So this will be 155 watts, 155.564 watts. So it will be 155.564, that is present in the option B. So yeah, these kind of questions also do come. So the this will be the correct answer of this question. Okay, I hope you have understood like how it will get scaled. So this, right, you can quickly revise once like once in a month or so that it comes into your factor, because gate can ask very basic question on this. Okay, so whatever I had discussed for power transformer and distribution transformer is written over here. Why we use power transformer, and why is just efficiency measured for power transformer, and why is alt efficiency measured for the distribution transformer. All the characteristics are given here. Okay, you can go through this. These are the comparison tables of power transformer and distribution transformer. You can go through, read about this. Okay, all the comparisons are given here. I will increase the size. Okay, so the power transformer is used in generating stations and substations. Distribution transformer will be installed near the consumer loads, near you. Okay, so what is energy efficiency? Why is power transformer focused more on reducing the transmission losses? Because it is connected near the generating station. So these are few critical points from where the interview questions can be asked. Okay, so that was basically it for this lecture, and in the next lecture we will study about testing of transformers. I hope you have enjoyed this video. If you did, make sure to hit the like button, make sure to comment down below, make sure to comment on the first video of this playlist. That will help us really out. Give a review in the first review, give a review of the course in the first video of the playlist. So yeah, that's it from my end. I hope you have enjoyed the lecture. I will see you in the next lecture. Until then, happy learning.